Mathematics Radio. Coming to you live from our secret headquarters by the bay. We're here to answer any of your mathematics questions you might have over this first Saturday in 2020. So, once again, the way this works, head on over to Twitter, tweet your math questions to @NightMathRadio, and I'll try to answer them live here on the air. As always, we're going to be with the best math help and the worst loops Apple has to offer. Now for tonight, I wasn't expecting to get too many questions. This is, after all, not really a school night for most people. The vacation's just coming to a close. Most people are still not yet back in the swing of things. So I thought I'd talk about trigonometry, because this is a big subject. It looks much harder than it is. What kicked this off was a fun question that came up earlier. So what I'd like to do is look at the fun question that got posted earlier, and then see if we can work back through and take a look at trig itself to see what's going on with trig, because trig's a field that appears to have a lot of moving parts, and it's not nearly as bad as it looks. So let's take a look at what's going on. So the question that's someone tweeted to me is this one. It says, answer this without using a calculator. 5 cosine 0 degrees minus 2 sine 30 degrees plus the square root of 3 cosine 30 degrees divided by tan 30 degrees times tan 60 degrees times cosine of 60 degrees plus 3 sine 29 degrees secant of 61 degrees. Now, this is looking a little hard to see on my paper here. Let me adjust the light a bit. There we go. That's a bit better. Now, how are we going to do this? Let's take a look at this for a minute. Now, the first thing to notice is that we've got a lot of 30 and 60 degrees in here. And the reason we do that a lot in trigonometry is that 30 degrees is one of the rare triangles where you actually know what the sines and cosines are in closed form. And when we say closed form, we mean we can write it down using radicals and numbers and generally not have to just rely on writing some horrible nonsense off your calculator and following with about that, ... approximately equal to. How can we do this? Well, let's look at the triangle for a second here. Now, let's start with an equilateral triangle. An equilateral triangle has 3 equal angles. Since the angles of a triangle always have to add up to 180 degrees, that means each one has to be 60 degrees. Let's think what happens when we cut one of these angles in half. Well, then we get a nice right triangle here, because this one splits it exactly in half. This is 30 degrees. And this is just one of the famous right triangles. This is called a 30, 60, 90 right triangle. Since this is an equilateral triangle, let's call this side 1. This, remember, is a bisector. Cuts it exactly in half. Remember, for an isosceles triangle, the angle bisector, the edge bisector, same thing. 1/2. And then we have this third side. And how do we get the third side? Well, we have to use Pythagoras' theorem. 1/2 squared plus whatever this third side is, call it s squared, has to equal to the hypotenuse squared, or 1 squared. So s squared plus 1/4 has to be equal to 1. S squared is therefore subtracting a quarter from both sides, 3/4. So s is equal to, taking a square root, the square root of 3 over 2. And now just looking at it, we can see what the sines and cosines are. So first of all, we have 5 cosine 0 degrees. So cosine 0 degrees is just 1. Why is that? Well, I'll talk about that just after this bit. So that's 5 minus 2 sine 30 degrees. Well, sine is opposite over hypotenuse. From 30 degrees, opposite is 1/2. Hypotenuse is 1. So that's just 1/2. Plus the square root of 3 times the cosine of 30 degrees. Well, cosine of 30 degrees is the square root of 3 over 2. Same thing. Adjacent over hypotenuse. And the hypotenuse is 1. Divided by, well, we've got the tangent of 30 degrees. That's opposite over adjacent. So 1/2 divided by square root of 3 over 2. Or 1 over the square root of 3. Which is better. Times the tangent of 60 degrees. Now, tangent of 60 degrees is again opposite over adjacent, but this time this is now the opposite, this is now the adjacent, so it's just the square root of 3. So these just cancel, and we'll talk about that more in a minute. Times finally cosine of 60 degrees, which is 1/2 over 1 times, which is just 1/2. Plus, now here we have a bit of a trick. We have 3 sine 29 degrees. And 29 degrees is not one of those angles that we know offhand. 29, unfortunately, really is a special one. So over here, we'll just write the secant as 1 over cosine. So this is going to be a bit trickier. We have to sit and think about what we're going to do there. Let's finish this bit over on the left where things are easy. Here we've got 5 minus 1 plus we have the square root of 3 times the square root of 3, which is just 3 over 2, so plus 3/2 divided by 1/2. So that's all nice and simple. What do we do with this thing over here? Well, cute thing to notice here, 61 and 29 should ring a bell. That's almost 60 and almost 30. And in particular, 61 plus 29 is 90. What that means is that in a right triangle with a 29 degree angle, the other angle is 61 degrees. So if in this thing we have, call this opposite, call this hypotenuse, the sine of 29 degrees is O over H on this picture. The cosine of 61 degrees is adjacent over hypotenuse, but the O is the adjacent from its point of view, so this is also over H. So this is plus 3 times O over H divided by O over H. And the O over H's cancel. So it turns out we don't need to know what the sine of 29 degrees is, which is good because it's horrible. Sine of 29 degrees is not something you want to meet in a dark alley. It's hideous. But since we're dividing it by essentially itself, we don't care. It's all very easy. Let's just work the rest of this out. 5 minus 1 is 4, or 8/2. 8/2 plus 3/2 is 11/2. Divided by 1/2, plus 3. 11/2 divided by 1/2 is just 11. Why? Because remember, dividing by 1/2 is the same as multiplying by 2. 2 times 11/2 is just 11. So this is 11 plus 3. So the answer is just 14. And now we're done. This is Nighttime Mathematics Radio. I'm gonna wait for about a minute here to see if anybody asks any questions on Twitter, and if not, I'm gonna flow into the fastest description of trigonometry you have ever seen. This is Nighttime Mathematics Radio. Once again, this is Nighttime Mathematics Radio. If you have any math questions that are on the tip of your tongue and you just can't figure out how to do them, come on over to Night Math Radio on Twitter. That's at Night Math Radio. Tweet me your questions. I'll try to answer them live on the air. This is Nighttime Mathematics Radio. This is Nighttime Mathematics Radio, coming to you live from our secret headquarters by the bay. Once again, if you have any math questions, you can tweet them to Night Math Radio on Twitter, and I'll try to answer them live on the air. Short of that, let's take a quick look at trigonometry, and by quick, I mean very quick. Now, trig is one of these subjects that gets involved very fast. A lot of people start working on trig and think they understand what's going on, and before they know it, suddenly there's unit circles everywhere, trig identities covering pages and pages of the book, and students are feeling like they got left behind somewhere. So let's take a look at what happened. Now, when trig first starts, it depends on something from geometry, which is the concept of similarity. Now remember, when you start in geometry, you first learn a lot about congruence. You learn about congruent figures. And the idea of congruent figures is if you know two figures are congruent, say this triangle ABC here, and this other triangle up here, which I'll call capital A, capital B, capital C. If you've got congruent figures, there's something fairly easy you could say, which is, well, since these figures are congruent, corresponding lengths are just equal. So if triangle ABC is congruent to triangle ABC, then the measure of A is equal to the measure of capital A, they have the same length. Measure of B is equal to measure of B, they have the same length, and so on. But then, that's sometimes too much to ask for. That works if you have side, side, side. You had all these ways to prove that things are congruent. You had side, side, side. You had side, angle, side was good enough. And then you had some that didn't work. You had things like side, side, angle. It's a messy ones. And particularly an interesting one, which is angle, angle, angle. And the problem is angle, angle, angle is that it's clearly not enough to prove congruence. Because the three angles of a triangle could be exactly the same, but it doesn't tell you very much about the scale of the whole thing. So this triangle, call it, let's call the side lengths this time, say, let's see, call them A, B, C, call this one capital A, B, C. Be a little more careful this time and label points rather than sides. This time we do not know, for example, that measure AB is equal to the measure of capital A, capital B. They can't be necessarily. You can see one's much bigger than the other. They have the same angles, but it's not the case that they have the same lengths. So in this case, we can't say the triangles are similar, are congruent. We have to say that they're similar. Now, what does it mean these triangles are similar? What that means is if I take any two of the sides and make a ratio out of them. So if I say, for example, measure AB divided by measure BC, that will be exactly the same as the corresponding ratio on the other triangle. So it isn't that the sides are the same, it's that they have the same proportions. This side to this side is the same proportion as this side to this side. And that's actually really a useful concept. Now, let's look specifically at right triangles. That's where trig really gets started. On a right triangle, we're given that one of the angles is a 90-degree angle. Now suppose we know any of the other angles. And following the ancient mathematics tradition that angles should use Greek letters, I'll call this angle alpha up here. Now, if this angle's alpha, we now know this one because the three interior angles of a triangle have to add up to 180 degrees. So alpha plus 90 plus this thing have to add up to 180. Well, this is already 90, so that means these two have to add up to 90 between them. So this has to be 90 minus alpha. So the thing you notice here is as soon as you know one other angle of a right triangle besides the right angle, you know all three angles, and in particular, any two right triangles that have that angle are similar. So all the ratios will be the same. And this is really where trig gets started, because what that means is if we call these sides, say, the opposite side, the adjacent side, and the hypotenuse being the long side, then all the possible ratios, opposite over hypotenuse, adjacent over hypotenuse, and opposite over adjacent, will be the same for every triangle that has that angle. And since it'll be the same for all those things, we can just make that a function of the angle. And each of these things can be a function of the angle. We write three functions, and they have names. Unfortunately, we write using three letters because math notation is weird and inconsistent sometimes. Sine alpha being opposite over hypotenuse, cosine alpha being adjacent over hypotenuse, and tangent alpha being opposite over adjacent. Now, up to this point, most people are pretty happy with trig. At this point, it's great, got it. Sine, cosine, and tangent, three ratios, life is good. But now you have to realize something. Now, these functions only make sense when alpha is between 0 and 90 degrees, and don't make sense for either 0 or 90 degrees. If alpha is 0 degrees, you don't have a right triangle, you have a line segment. If alpha is 90 degrees, again, you don't have a triangle, you have a line segment. So, how can we make this a function that makes sense over more than that? And this is the place where most students begin to get wobbly on trig. We play a trick. Here's the way this trick works. We first say, let's consider something that at first blush looks totally different. Let's look at a circle of radius 1. So it goes through this point here, 1, 0. Goes through this point up here, say about there at 0, 1. Goes through this point back here at -1, 0. And through this one down here at 0, -1. And you'll see me freehand a circle, which is not one of my job skills, as you'll see in a minute. So here we have a circle of radius 1. And this is famously called the unit circle. Not because it's good at fighting Daleks, because unit's another name for 1. Now let's look at this point here. We would like to know the x and y coordinates of it. I'll call this angle here, moving up counterclockwise from the x-axis, alpha. And we notice, aha, this is a right triangle of side alpha. And moreover, these sides have meanings up here. This length of the triangle is the x-coordinate of that point that I drew there. This is the y-coordinate, and this is 1. So the x-coordinate is, from the point of view of alpha, adjacent. And since the hypotenuse is 1, adjacent's the same thing as adjacent over hypotenuse, so this is just cosine alpha. Moreover, the y distance there is opposite alpha. So opposite over hypotenuse is, again, opposite over 1. So that's sine alpha. So as long as we're at a point here in quadrant 1, that point is just cosine alpha, sine alpha. That's really handy. And now we play one of the great stupid tricks that runs through all of mathematics. We defined earlier sine x and cosine x up here. Sine alpha and cosine alpha, I should say, in terms of a right triangle, and then we said, oh, as long as you're in the first quadrant of the unit circle, that's also just the coordinate values of a point in the first quadrant of the unit circle. And now we say, actually, I like that definition better. Rather than making that a consequence of the earlier definition in terms of sines and in terms of opposites and adjacents of right triangles, why don't I make this the definition of cosine alpha comma sine alpha? Why don't I say cosine alpha is the x-coordinate of a point on the unit circle if you move alpha around in the counterclockwise direction starting at the x-axis, and sine is the y value of a point on the unit circle moving alpha around in a counterclockwise direction starting at the x-axis. Why is that useful? Well, it means the same thing as long as you're in the unit circle here, as long as you're in quadrant 1. Moreover, it means the same thing with respect to right triangles, because any right triangle with some angle you can draw a version of here in the first quadrant, and it will mean exactly the same thing as it did before. But the unit circle definition also works for values of alpha outside of the first quadrant. If I want to know what cosine of 0 was, for example, before I just had to hurt my head, because if I'm trying to draw it with a triangle, that's a triangle that looks like this. And I have trouble telling what the opposite, adjacent, and hypotenuse are of that. I have no idea what that is. But on the unit circle, I know exactly what this point is. I already labeled it. It's 1, 0. So the cosine must just be the x value. Cosine of 0 is 1. How about sine? Well, sine of 0 must be 0, because it's right there. How about up here? Aha. Well, up here at 90 degrees, cosine of 90 degrees must just be 0, because that's the x value of a point 90 degrees counterclockwise from the x-axis. It's just a point on the y-axis, where x is 0, and y is 1, because this is still the unit circle. How about over here in quadrant 2? What if we have an alpha that's bigger than? What if we have an alpha that's bigger than 90 degrees? What if we're over here? Well, this little angle down here is 180 minus alpha, which is still a net value in the unit circle. Sorry, between 0 and 90. So for this point, well, the x value is now negative. You can see that. We're in quadrant 2. So this value here is cosine of 180 degrees minus alpha in the minus direction, comma, sine of 180 minus alpha. So again, that value there is, I didn't plan that very well, cosine of 180 degrees minus alpha, comma, sine of 180 degrees minus alpha, except the cosine is negative because we're off in that direction, and that tells us what we mean by cosines and sines when alpha's in the second quadrant. It's just cosine and sine of 180 minus that value, except now the cosine value is negative and the sine value is still positive. And you get the same thing as you go around. Cosine of 180 is now well-defined. It's minus 1. Sine of 180 is still well-defined. It's 0. And you can play this game all the way around in all 4 quadrants. Up here in the first quadrant, you have sine alpha, comma, cosine alpha, both positive. Up here you have cosine alpha less than 0, sine alpha greater than 0. Down here, both of them are negative because x and y are both negative, so you have cosine alpha less than 0, sine alpha less than 0. And finally, over here, we have cosine is now positive again, because in the fourth quadrant, the x value is positive, and sine alpha is still negative because you're still below the x-axis. And so now sine and cosine make sense for any angle you plug in. Not only that, but if you go past 360 degrees, the function repeats because you've just gone around the circle once. So the function is 360 degrees periodic, or if you're using radians, 2 pi periodic. So this function repeats over and over and over again. That's the real power of sine and cosine. It turns out the main use of sine and cosine isn't just the geometric use that you see. The other main use is representing things that are oscillating. And as you go on into calculus and into differential equations, you'll see this is the easiest way for something to oscillate. Lots and lots of things oscillate this way. In fact, small oscillations of almost any oscillatory behavior look like this. Whether you're talking about businesses going through boom and bust cycles, whether you're talking about a spring bouncing up and down, whether you're talking about a pendulum swinging back and forth, almost anything that oscillates can be represented using sine and cosine. And that's probably the single most important purpose of sine and cosine in mathematics. So that's how we get to the unit circle. The key thing here is that the definition gets switched. The moment you start thinking about the unit circle, you realize that the unit circle definition is a much more powerful definition than the old opposite over hypotenuse, adjacent over hypotenuse, opposite over adjacent definitions. In fact, the cool thing is it also makes tangent mean something interesting. Because tangent, remember, we said was opposite over adjacent up here, but if you look at sine alpha divided by cosine alpha, that's equal to opposite over hypotenuse divided by adjacent over hypotenuse. That's just fraction division, so that's opposite over hypotenuse times hypotenuse over adjacent. Cancel hypotenuses. That's opposite over adjacent, which is tangent. So in other words, tangent theta is just sine over cosine, or on the unit circle, that's y over x. And y over x is interesting. Why is it interesting? Well, because it's literally rise over run. That's the slope of that line going from the origin out to that point on the unit circle. And now its behavior, when you graph it, makes sense. It starts at 0, becomes 1 when you get to 45 degrees, then blows up when you get to 90. Because after all, there is no slope for a line that goes up and down. You can't define a slope that way. So it gets enormous, blows up to infinity. Then the moment you get past 90 degrees, it's suddenly huge and negative, because now this line is sloping down very quickly, not up very quickly. Then it goes all the way to -1 when we get to 135 degrees. Then all the way back to 0 again when you get to 180 degrees. And the cool thing is, looking at the way I draw my pen, if you're talking about a slope, you can't tell whether you're looking to the left or looking to the right. So the tangent isn't 360 degrees periodic like sine and cosine are. It's only 180 degrees periodic. Because being a completely flat line looking to the left and a completely flat line looking to the right doesn't change the slope. They both have the same slope. That's slope 0. So the thing repeats again every 180 degrees. And that's why the tangent has that shape that you know so well. This is Nighttime Mathematics Radio. Once again, if you have any math questions, feel free to tweet them to me at Night Math Radio on Twitter. Failing that, we'll probably end the episode early in about 5-10 minutes. This is Nighttime Mathematics Radio. everybody. It's a bit of a quiet night, which makes sense after all. This is the very last holiday weekend before we get back into the swing of things next week with the school year beginning in most places. So for the vote, we're going to end the show early. This is Nighttime Mathematics Radio, coming to you from our secret headquarters by the base, signing out. Good night, everybody.